Hello and welcome to this lecture on GGPs. That stands for Generalized Geometric Programming. In this one, we're going to introduce some mathematical recipes, I would say, that we need to define what a GGP is. That is, as in the previous lecture, we introduced polynomials and monomials. We're going to introduce in this one what a generalized polynomial is. Next off, we're going to see how a GGP is formulated and another instance of an optimization program called mixed integer geometric program. Next, we're going to see how to formulate a GGP as a GP, and thus it could be seen as a convex program. That is to say, we can use the change of variable we used in the previous lecture to convert a GP to a convex form. So a two-stage process. First a GGP to a GP and then a GP in convex form. Later on we're going to see some applications of geometric programming such as floor planning, power control, and digital circuit design. So without further ado, let's get started. So before we define what a GGP is, similar to the previous lecture, we have to introduce some mathematical functions that have to do directly with the problem. We're going to define something called generalized polynomials. So as a quick reminder, a polynomial is a sum of monomials. That being said, as in the previous lecture, a polynomial takes in a vector in Rn and returns a scalar, where the domain of f is Rn++, that is, all the entries of x have to be positive, and the function will look something like this. If it is of order k, ck, x1, power alpha, 1k, down to xn to the power alpha nk, where my alpha I k's are in R, and my ck is positive. So likewise, a generalized polynomial is a composition of polynomials. That is, you can grab a bunch of polynomials and do the following operations on them so that you have what is called a generalized polynomial. So if you grab two polynomials and you add them, multiply, exponentiate to something that is positive, and even take max of polynomials, well, you have what is called a generalized polynomial. Now let me show you some examples. The following is a polynomial, right? And so is this. So those two are polynomials. That being said, if I take the max of those, we have what is called the generalized polynomial. Also, you can grab all this, raise it to the power, something that is positive, let's say pi. This is also a generalized polynomial. So any further operations on those simpler operations is also a generalized polynomial. So that being said, generalized polynomials are closed under addition, multiplication, exponentiation, and maximum of simpler generalized polynomials. So that being said, I could also come here and add a polynomial as such, and also grab all this guy and multiply by another polynomial, or by max of polynomials, max of, let's say, x1, x2, x3, and maybe x3 to the power e, x4 to the power root 2, and so on. You can make it as complicated as possible. And you can also come here and take a power, c squared, for example. So all this is generalized polynomials because it's made up from simpler polynomials with the following operations. Now there's another way of seeing this, i.e. composition of polynomials. So let me go down here. Since we know now what a polynomial is and a generalized polynomial is, we said in the previous lecture that polynomials are closed under products, sums, and multiplication by non-negative scalars. If I grab, let's say, p polynomials and I pass them as arguments to a multidimensional polynomial, or just simply polynomial. So let's say I have a function that is p, x1 down to xp. So this is a polynomial that takes p arguments and returns a scalar. We all know what polynomials are. They're simply sum of exponents of x, scaled exponents of x in 1D, right? So ak x power k. Then dimensions, you're allowed to multiply terms, so you could allow interactions between terms. So x1 square, x2 plus 3x2, x3 plus 5, let's say xp square, and so on, right? What you're not allowed to do is to set fractional exponents. In that case, you're generalizing your polynomial to a posynomial. If I come here and insert a half right here, p is no longer a polynomial, it's a posynomial. Now, why am I talking about polynomials here? Well, an equivalent way of saying polynomials are closed under products, sums, and non-negative scaling. You can see it as one simple thing. So if you pass polynomials as arguments to a polynomial, so let's put here f1x down to fp of x as arguments, right? So in this simple example, we will have f1x square f2 of x plus 3 f2 of x, f3 of x plus 5 fp of x squared, and so on. Then this guy is a polynomial because all we did was a series of products, sums, so products, f1 with itself, so f squared, then f2, and here we've got f2, f3, and so on. All we did was a series of products, sums, and non-negative scaling, and thus this is a polynomial. Now, if p happens to be a polynomial, then this guy is no longer a polynomial, it's a generalized polynomial. So if I say, I'm going to indicate a note that p is a polynomial, and this is why passing polynomials as arguments will reserve my output as a polynomial. However, if I have another function g that is a polynomial, so an example would be, I don't know, x1 half x2. Note here the fractional exponents, plus 3x2 inverse x3. Also negative exponents, plus 5xp to the power pi maybe, and so on. Then if I pass polynomials to this function as arguments, so in that case I will have, maybe in this simple example, I'll have an f1 half f2 plus 3 f2 inverse f3 plus 5 fp to the power pi. This guy is now, so that's another compact way of seeing stuff. All you have to do is to remember, if I pass polynomials to a polynomial, then I get a polynomial. If I pass polynomials to a polynomial, then I get a generalized polynomial. Oh, and by the way, g shouldn't have negative exponents. They could be fractional, but they have to be positive. That being said, this -1 here is a mistake. So correction, I'm going to replace it with a +1, and here I'm going to have a +1. So not any polynomial, g shouldn't be any polynomial. It should be polynomial with non-negative exponents. So I'm going to write this constraint here, non-negative exponents. Because clearly, if I divide a polynomial with another polynomial, the outcome need not to be a polynomial. Now that we defined what generalized polynomials are, let's formulate a generalized geometric program. So we're going to minimize, the same as in geometric programs, cost f0 of x subject to the following constraints, inequality and equality. So I'm going to copy them, nothing has changed, except for one thing which is clear. So now those two functions are not only polynomials, they have to be generalized polynomials. And this guy right here, a monomial. So in the extreme case, if those two are, if f0 and the fi's are polynomials, then we're back to geometric programming, right? As you can see here. Now this is, it looks simple, but it's really not simple. Actually, this is a highly nonlinear constrained optimization problem. So that's simply what a GGP is. The next thing we're going to talk about is something really interesting. So like we saw here, a GP in polynomial form, that is the generic form, which is not convex, we saw a certain conversion to a GP in convex form. That is, with a simple change of variable, we can write a GP in convex form. Now, is there something equivalent here? We're going to see indeed there's something we can say. We can actually express a GGP as a GP. So I'm going to write the problem down with a bit of change of notations. This time I'll minimize h0 of x, subject to my hi is less than 1, and my gi's are equal to 1. So in a GGP, those guys are generalized polynomials, and this guy is a monomial. So if I want to convert a GGP to a GP, I don't have a problem with my gi's, right? Because they're already monomials. What I do have a problem with is my h. My h's are generalized polynomials. So how do I convert them to a polynomial? Well, we're going to use a standard trick right here that we used thoroughly throughout the lectures. That is, first, we're going to bound the cost by, let's say, t. So instead of minimizing h0, I'm going to minimize t, right? And we're going to express this guy as one of the constraints. Note that this constraint is the equivalent of just saying t minus 1, h0 of x less than 1. Now this guy is a generalized polynomial. Since I'm multiplying with t minus 1, which is one of the variables now in the problem, along with x, the whole thing is a generalized polynomial, and hence I only have generalized polynomials in my constraints. So I'm going to rewrite the following as such. Here's the additional constraint. Note that all those guys right here are generalized polynomials, and hence I could express them as a polynomial of polynomials, right? That is, each one of my hi's, let's grab one polynomial and a similar argument will be held on the others. So I'm going to grab one polynomial, hi of x, and I'm going to say that it is phi I of fi1 of x, comma, fi, say, k of x. So that being said, we're seeing one polynomial as a composition through a polynomial function, which is phi I, of simpler polynomial functions. Each one of those is also a polynomial, right? So when I say this is less than 1, what does that mean? Could we express this in a different manner? Well, yes. This is the equivalent of saying each one of my fi's, which is a polynomial, is less than a ti. So t1 or ti1 down to ikx less than tik, right? And since the ti's are upper bounds of the fi's, I could just go ahead and say phi I ti1 tik less than 1. Now all those constraints, all those k plus 1 constraints, which are simply polynomials, right? Because this is a polynomial, and to have a polynomial less than 1, I could rewrite this as ti1 inverse fi1 of x less than 1, polynomial, no problem. And likewise here, right? And here I've got the 1, and this is a polynomial, so no problem. So what I mean to say is that I have polynomials on my left-hand side and 1s on the right-hand side. So I'm replacing a generalized polynomial, hi of x less than 1, with k plus 1 polynomial only constraints, right? Now to see why this simple constraint is the equivalent of those k plus 1 constraints, let's denote this statement by 1, and this is 2. Now let's prove one sense first. Let's assume 2 is true, and let's try to prove 1. So if 2 is true, now we're going to exploit the fact that phi I, since phi i's, all my phi i's are polynomials with positive exponents and non-negative scalars, then phi I has to be monotone, non-decreasing in each and every one of the arguments t1 down till tk, right? This implies that if all my fik's are less than terms tik's, this will give me that phi I, ti1 down to tik is simply less than 1. We just use the fact that phi i's are monotone, non-decreasing. Now, the definition will imply that the lower arguments, fi1 of x down to fik of x, since those arguments are lower, then this function cannot exceed the original ti1 down to tik, which is in turn less than 1. And there you have it. 1 is proved. Using this, less than this. Let's assume 1 is true. How do we prove 2? That is to say, my phi i's fi1 of x down to fik of x is less than 1, right? Now if I choose my tik's to be my fik's, we simply get phi I ti1 tik less than 1 with ti1 equal to fi1 and tik equal to fik, right? Which implies that 2 is correct. So what does that mean? That means every generalized polynomial is being expressed as k plus 1 polynomials. That being said, I don't have any generalized polynomials anymore. All I see is polynomials less than 1. That is, we get a GP. Now, how many constraints do I get in total? Do the math. We've got here m constraints, right? So m constraints plus 1, m plus 1, y plus 1. This is an additional constraint. So those are m plus 1. And each one of those are giving me k plus 1 equivalent constraints. So in total, I will get a problem, which is a GP minimizing just t, subject to k plus 1 times m plus 1 polynomials less than 1. And the monomials are left untouched. So gi of x is equal to 1, where I have p such constraints. One really common example is floor planning. So in floor planning, you've got certain rectangles or rooms, let's say. So this is a rectangle with height h1 and width w1. Say this is another rectangle 2 more times. Let's start this here. So h2 w2, h3 w3, and h4 w4. So I'm given those 4 rectangles, let's say, and our problem is to find the smallest rectangle that fits all the smaller rectangles. So the rectangle on the outside with width w and height h, given some limitations. Now what are those limitations? Stack a line here as well. So the problem here is that we want to find the minimum area that fits all the rectangles, so minimize the area HW, right? Subject to some limitations. We are given that each and every one of those smaller rectangles have fixed areas, or given or desired areas. So area A1, A2, A3, and A4. So those give me 4 monomial equality constraints. So HK, WK is equal to AK, right? Where K is going from 1 to 4, right? I've also inserted this line here on purpose. This means that those 2 rectangles over here, the heights of A3 and of rectangle 3 and 4 should not exceed this part over here. And similarly, the heights of H1 and H2 must not exceed this part right here. So how do we reflect this? We can use the max function right here. So max H1, H2, right? Max H1 and H2. This constrains this part right here, and the part right here similarly is max H3 and H4 should be less than H. Okay, this guarantees that all the four boxes have heights fitting those two rectangles. Also, we have a width constraint. That is, we see that W1 plus W2 should not exceed W. So W1 plus W2 should not exceed W's. Likewise, W3 and W4 should not exceed W. Right? Those two could formulate one max constraint. That is, the max W1 plus W2 with W3 plus W4 should be less than W. So I could erase this and just copy this. And let's say I'm given certain aspect ratios on each and every one of the four rectangles. That being said, I can bound my HI over WI between alpha and beta. Alpha I and beta I, let's say. So this problem right here is a GGP. Why? This is a monomial, and hence a polynomial, and hence a generalized polynomial, right? Easy to see. The equality constraints form monomials. How? Just divide by AK. So minimize F0 of my variables. What are my variables? HW, W1 through W4, and H1 through H4. This is equal to HW, as we saw, the cost. Subject to, we're going to divide on both sides by AK. We get AK minus 1, HK, WK is equal to 1. That being said, this guy is a monomial, so no problem here. Now the max is, we have max of simpler terms, of linear terms. Linear is a particular case of a polynomial, and we mentioned previously that we can do such compositions using the max of simpler polynomials. So anything with max, exponentiation, multiplication, and addition is okay to formulate generalized polynomials. So keeping that in mind, all we did was max of polynomials, if you will, with one terms each. And thus, this guy right here is a polynomial. To get a 1 on the right-hand side, we divide by h. So we get h minus 1 max h1, h2. Be careful, h is a variable, not a constant. So same h minus 1 max h3, h4 is less than 1. Now, all this is a generalized polynomial. Why? This is a polynomial. We multiplied it by a polynomial, h minus 1. Then we added it to another generalized polynomial. And we know that generalized polynomials are closed under addition. So this guy right here is a generalized polynomial. And with a similar manipulation you get, and this guy holding a similar argument is also a generalized polynomial. Now the last constraint is very easy. When we talked about volume maximization, we had a similar constraint right here. All you have to do is split it to two inequalities as such, where both are polynomials. And that's it, you're done. So right here, this one was discussed in the previous lecture. Okay, so this is a full example on GGPs. I'm going to give another example which I should have given in the previous lecture. It's the power control problem. So this is a GP, so it's not a GGP. Well, strictly speaking, a GP is a GGP, but not the other way around. All I'm saying is the power control problem is only a GP. So what is the power control problem? This is a telecommunication problem where I've got n transmitters. So TX is transmitter, and I've also got n receivers. So let me just, so this TX1, TX2, TXI, TXJ, right? Likewise. So the problem tells us that each of the transmitters transmit at power levels P1, P2 down to Pn, okay? So the game here is that transmitter I has power budget PI. Now, ideally, we desire that transmitter I transmits to receiver I, and that's it. So transmitter 1 talks to receiver 1, transmitter 2 talks to receiver 2, but that's not the case in real world. So what happens is that while transmitter I talks to receiver I not only listens from transmitter I, but also listens from all other transmitters. That is, there is a certain leakage from transmitter 1 to receiver I, transmitter 2 to receiver I, transmitter N to receiver I. Okay? The gain from transmitter I towards receiver I is going to be optimized. That is, receiver I is said to be good enough if the gain from transmitter I is sufficiently larger than all other gains. And where does this gain come from? So this is the channel between two nodes. That being said, transmitter I talks to receiver J, and there's a certain channel between them with gain Gij. So from here till here, there's a G1, G1, 2, and so on. So another note here is that channel between Txi and Rxj is simply Gij. So if I focus at receiver J, in an ideal world, J should receive Gjj times Pj. This is the power received from transmitter J at receiver I. But this is not the case. Receiver J not only receives Gjj times Pj, this is from Txj, but from all other Tx's. So from all other transmitters. And how do we model that? What is the undesired, let's say, power received? It is from all transmitters other than J, right? So it will be Gj1 times P1 plus Gj2 times P2 plus, now we're going to have to exclude this guy because this is not part of the undesired signal or the interference. So Gj, then it's J minus 1, Pj minus 1, then skip the Pj, right? Because this is what we want. So there's nothing here. Then Gjj plus 1, Pj plus 1, all the way down to Gjn, Pn, right? So this could be expressed compactly as a sum where k is not j, Gjk, Pk. Simple as that, right? So this guy is usually referred to as the interference term, right? It's all other undesired powers. This guy is called the interference. And therefore, in communication systems, we usually care about an important ratio called the SINR. So the signal to interference noise ratio. That is equal to the desired power in the numerator. That is, in our case, so an SINR for which receiver? For receiver J. In our case, it is G, Jj, Pj, so the desired power over the interference plus the noise power at receiver J. So noise power comes from equipment, from various equipment used at receiver J, from imperfections, change of temperature, so on. So 3 parts in this expression. What we desire is that this expression has at least a certain level. So it has a lower bound. We do not want to be worse than a certain threshold. We desire that this guy is at least a given minimum. So S min. Since we're talking about power budget, so we're restricted with some power limitations because you cannot expect to use as much power as you want. So each of the transmitted power at each transmitter is bounded between a Pj min and a Pj max, right? So now your problem could be expressed as follows. Now it depends what you want. Do you want to maximize SINR or do you want to minimize the total power consumption? Depends what you're doing. Let's formulate this problem then. So we're going to minimize the total power consumption. So minimize P1 plus Pn, all the power. You can also do a variation of this part. You can do a weighted power, so W1 P1 down to Wn Pn. It depends if you want to focus on a certain transmitter. A certain transmitter has more preference than the other, and so on. We're minimizing this subject to this budget right here. So each of the PJs is between a PJ min and a PJ max. And the SINR, we need to guarantee a minimum performance. So this ratio is greater than S min. I'm going to write it here. Sorry about that. This should be a K right here. It's greater than S min. This is for all J's from 1 till N. And so is this. Okay, so this problem right here, it looks easy at first sight. So here we've got a linear cos. Linear is a particular instance of a polynomial, right? So this is linear slash a polynomial, right? Polynomial with n terms, right? And this constraint right here that you see is also linear. We saw it previously. Those bounds, as such, lower and upper bound, could be easily transformed to a polynomial inequality. So on the left-hand side, I get a polynomial. On the right-hand side, I get a 1. So here, I'm going to write polynomial inequalities, right? Now, the last inequality is a bit tricky. You might not get it at first, but it's okay. So we've got a polynomial in the denominator and a monomial in the numerator, right? What could be done here? Usually, a trick for that would be to take the reciprocal on both sides. So this is the equivalent of 1 over less than 1 over. So you get a GJK, pk plus sigma k is less than over GJJ is less than 1 over S min. This is a polynomial, and this is a monomial. And we know that if we divide a polynomial by a monomial, then the outcome is a polynomial, right? Multiply by S min on both sides, so times S min. You just get a scalar here, S min times a polynomial, which is also a polynomial, is less than 1. So these guys are also a polynomial, and hence this inequality also forms polynomial inequalities. So polynomial inequalities with a polynomial cost, no equality constraints, that's okay. The problem is now a GP. Right, so that's it for this example on power control. There's really way more examples that could be given on GGPs. I'm not going to discuss them here in details. I'm just going to give a bit of an insight. It's when you're designing digital circuits. So I've got a certain circuit with some flip-flops as input and flip-flops as output. Let's say this block right here represents my input flip-flops, and this guy right here is my output flip-flops. So my input is basically here, and over here I've got my output. Now, what's in between is a combination of some logical blocks. So some certain gates, I would say. So let's say right here, I've got a logic block, right? It's composed of smaller logic blocks, right? So let's say I've got a gate right here, a gate right here, 1 here, 4, 5, and a 6. Okay? And they're connected as such. It's just an example. Okay? So I just want to show you how is GP or GGP is related to this. Well, when you're designing a logical block as such, you're displacing gates as such, you have some constraints in life. The easiest to name are circuit area. Power is another constraint, and the total delay in the circuit is another constraint, right? So when I mean delay, I mean the propagation delay from, let's say, this point to out. In that case, you'd have to do a study what if the signal passes, takes this route right here, or this route right here, or even this one, right? Now, in any case, there's a certain study on how much delay, or the worst case delay of the circuit I might face. When you want to do a serious study of the delay, you have to lay out all the, let's say, passive components inside each gate. So let's say each one of those 1, 2, 3, 4, 5, 6 gates looks like this in reality. I've got a capacitor here, there's a Cn, another one here. This is just an example. It might not reflect real life gates, but this is one example of a RC gate model. Got a certain switch, got an RC component, the ground, and a C to the load. So a CI load, CI, these are called intrinsic capacitors. Those are the input capacitors, and this is an input resistor. Also got a switch right here, the ground. If you do a bit of circuit analysis, the delay in this gate happens to be of the following form. So it's constant alpha multiplied by RICIN plus RI, the sum of all CIN. Now, as you can see, if you were to pick the values that would minimize your delay, you've got a polynomial in R and C, right? So that being said, the delay in one path is a polynomial. Therefore, when you want to minimize with respect to the delay, then your cost function is a polynomial, and therefore you will be faced with a GP. Now, the maximum of the delays, if you want to minimize the max of all delays, you take the max of all DIs, then the max of all, say D1 down to Dn, this guy is a generalized polynomial, because we said the max of polynomials is a generalized polynomial, and hence the cost function will reflect a GGP problem. Now, this is just one example. Other examples could be the area and the power, where you want to minimize the area, minimize the total consumed power, and so on. All those problems are also GGPs. So that's all the examples that I have to give in this lecture. Let's go back here to the problem formulation of a GGP. We can define a very similar type of problem called the mixed integer geometric program. So you can just add one more constraint right here that obligates that all your decision variables, x's, belong to a discrete set. So you'd want to minimize a generalized polynomial subject to generalized polynomials less than 1 and monomials equal to 1. Got m of those and p of those, right? But this time, all your xi's belong to discrete sets, di's. Example could be di is 1, 2, 3, etc. Could be all powers of 2, and so on. Here your I goes from 1, let's say, to k. Note that k could be 1 or could be n. Well, if k is equal to 1, only one variable is discrete, while the others could be continuous. Well, in that case, it's still a mixed integer geometric program. It suffices that only one decision variable is discrete. Now, these type of problems are very hard to solve for their exact solution. Some methods make approximations or compromises to get an acceptable solution. There's other methods that tackle the exact problem, but there is no guarantee of optimality. Those are called heuristic methods. Heuristic as in it's a trial and error type of method. It attempts to find a good approximate solution very quickly. It happens that if you want to solve for this problem, get the exact solution, it could take you days to reach the solution on a computer, meaning that global methods that to get the exact solution with no approximations or no relaxations can be extremely slow. Right, so in this one, we saw what generalized polynomials are, how a GGP is formulated, followed by mixed integer geometric programs. Then we saw how to convert a GGP to a GP, and then we gave 3 examples that are floor planning, power control, and digital circuit design. I hope you enjoyed this lecture. I hope it was beneficial to anyone watching this video. If you found it useful, please like the video and leave a comment if you have any questions. Subscribe to the channel and hit the notification button if you wish to receive further updates about the channel and similar lectures. That's it for this one, and I'll see you in the next one.